2 trillion galaxies. That is the current estimate. Not billion, trillion. 2 trillion galaxies in the observable universe, each one containing hundreds of billions of stars, most of those stars orbited by planets, a meaningful fraction of those planets sitting in the habitable zone where liquid water can exist on the surface. The number of potentially habitable worlds in the observable universe is a number so large that writing it out would take more digits than this sentence has words. The math has been done. The numbers have been checked. The universe has had 13.8 billion years to produce intelligent life. That is 3 times longer than Earth has existed. 3 times longer than it took for single-celled bacteria to become you. If intelligent civilizations arise on even a tiny fraction of those worlds, the galaxy should be teeming with them. Not might be, should be. 60 years of listening. The most sensitive radio telescopes ever built, scanning millions of frequencies, pointed at thousands of stars. 60 years. And in all that time, across all that sky, we have detected exactly 0 confirmed signals from another civilization. Either we are the only intelligent species in a universe of 2 trillion galaxies, or everyone else has learned to stay quiet. Over the next 45 minutes, you are going to understand why physicists believe the second option is more terrifying than the first. And by the end, you will know why some of them think we have already made a mistake that cannot be undone. In the summer of 1950, the physicist Enrico Fermi was walking to lunch at Los Alamos National Laboratory with 3 colleagues. Edward Teller, the man who would later be called the father of the hydrogen bomb, Emil Konopinski, a nuclear physicist, and Herbert York, who would go on to become the first director of the Lawrence Livermore National Laboratory. These were not dreamers. These were the men who had built the atomic bomb. They dealt in hard numbers, verifiable outcomes, things that either worked or didn't. They had been joking about a cartoon in the New Yorker, something about aliens stealing trash cans from New York City. The conversation drifted, the way conversations among physicists tend to drift, from flying saucers to the plausibility of faster-than-light travel to the age of the galaxy. By the time they sat down to eat, Fermi had gone quiet. He was doing arithmetic in his head. Then, in the middle of lunch, with no preamble, he asked, "Where is everybody?" His colleagues laughed, but Fermi was not joking. The calculation he had just run was simple and devastating. The Milky Way galaxy is roughly 10 billion years old. It contains somewhere between 100 billion and 400 billion stars. Even if intelligent civilizations are extraordinarily rare, even if only 1 in every million stars produces one, that still means there should be hundreds of thousands of civilizations in our galaxy alone. And given the age of the galaxy, even at speeds far below the speed of light, using technology not much more advanced than what we have today, any one of those civilizations would have had enough time to visit or colonize every star system in the Milky Way. Not once, multiple times. The galaxy should be crowded. It should be noisy. There should be signals everywhere, probes everywhere, evidence of engineering on scales we can barely imagine. And yet, there is nothing. No signals, no probes, no megastructures, no evidence that any civilization has ever existed anywhere except on this one small planet, orbiting this one unremarkable star, in the outer arm of this one unremarkable galaxy. So where is everybody? Nobody at the table had an answer. Edward Teller, who had helped design weapons capable of ending civilization, could not explain why no civilization in 10 billion years had managed to make itself known. Nobody in the 75 years since has had a definitive answer either. The question became the most famous unsolved problem in astrophysics. It became known as the Fermi paradox, and it has haunted every serious attempt to understand our place in the universe. 11 years later, a young astronomer named Frank Drake decided to stop theorizing and start listening. In 1960, at the Green Bank Observatory in West Virginia, Drake pointed a 26-meter radio telescope at 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for signals at 1,420 megahertz, the frequency of hydrogen. the most abundant element in the universe. The frequency that any civilization with a basic understanding of physics would know about. If there was a universal channel, a cosmic default frequency where civilizations might broadcast, this was it. He heard nothing. But the attempt changed everything. The following year, Drake convened a small meeting of 10 scientists at Green Bank to discuss the search for extraterrestrial intelligence. To give the meeting structure, he wrote a simple equation on the blackboard, a formula that multiplied together 7 factors: the rate of star formation in the galaxy, the fraction of stars with planets, the fraction of those planets that could support life, the fraction where life actually develops, the fraction where intelligence emerges, the fraction that develops detectable technology, and the average lifespan of such civilizations. Multiply them together and you get N, the number of communicating civilizations in our galaxy right now. The Drake equation became the foundational framework of SETI, the search for extraterrestrial intelligence. It was elegant. It was also, as astronomer Jill Tarter later described it, a wonderful way to organize our ignorance. Because in 1961, most of the variables were unknown. The equation did not produce an answer. It produced a map of everything we did not know. But even the most pessimistic estimates, plugging in the most conservative numbers at every stage, suggested there should be at least a handful of detectable civilizations in the Milky Way. And the Milky Way is just one galaxy, out of 2 trillion. Drake kept listening. Others joined him. SETI became a formal scientific discipline. Radio telescopes scanned the sky year after year, decade after decade, across millions of channels simultaneously. The technology improved exponentially. By the 2020s, the Breakthrough Listen initiative, funded by $100 million from billionaire Yuri Milner, was scanning more stars across a wider range of frequencies than all previous SETI searches combined. The silence held. In all those decades, across all those searches, the single most promising moment came on a summer night in 1977. At a radio telescope in Ohio that most people have never heard of. Jerry Eman was a volunteer researcher at the Big Ear Radio Telescope, a flat, football field-sized reflector operated by Ohio State University as part of their SETI program. On August 15, 1977, Eman was reviewing computer printouts of the telescope's data from the previous few days, columns of numbers representing signal strength across various frequencies, when something stopped him cold. A burst of radio energy at 1,420 megahertz, the hydrogen frequency, the exact channel Frank Drake had been listening on 17 years earlier. The signal was 30 times louder than the background noise of space. It lasted 72 seconds, the maximum duration the Big Ear telescope could observe a fixed point in the sky before Earth's rotation moved it out of range. The signal rose in intensity as the telescope swept toward the source, peaked, and then faded exactly as a genuine extraterrestrial signal should. Eman grabbed a red pen and circled the alphanumeric sequence on the printout, 6EQUJ5. Next to it, he wrote a single word that became the signal's permanent name. For 48 years, the signal that Eman found has been the strongest candidate for an extraterrestrial transmission in the history of SETI. It was not terrestrial interference, that was ruled out. It was not a satellite, the frequency was wrong. It matched no known natural source. It appeared once, at the exact frequency a civilization would logically choose, with the exact profile a real signal would have. And it never repeated. Eman and dozens of other astronomers pointed telescopes at the same patch of sky hundreds of times in the months and years that followed. They used more sensitive equipment. They listened for longer periods. They searched across wider frequency bands. Nothing. The signal appeared once in 72 seconds and vanished from the universe. In 2025, researchers from the University of Puerto Rico proposed the best explanation to date: a magnetar, a neutron star with an extraordinarily powerful magnetic field, may have triggered a brief natural maser in a nearby hydrogen cloud, producing a one-time burst at exactly the frequency SETI was monitoring. The signal was probably natural. Probably. The research team was careful to say the case is not closed. The original data from 1977 is still being analyzed, and the full archives of the Big Ear telescope are scheduled for public release in 2027, on the 50th anniversary. But what matters for our story is not whether the signal was alien. What matters is that in 60 years of searching, with increasingly powerful technology, scanning millions of frequencies across thousands of stars, this single event, 72 seconds long, never repeated, probably natural, is the best we have found. One signal, in 60 years, in a universe of 2 trillion galaxies. Fermi's question remained unanswered. Where is everybody? And while SETI was listening, while radio telescopes scanned the sky in silence, humanity was doing something else entirely. Something that, depending on which physicist you ask, was either the most hopeful gesture in the history of our species or the most catastrophically reckless. We were not just listening, we were talking. On November 16, 1974, a team led by Frank Drake and Carl Sagan gathered at the Arecibo Observatory in Puerto Rico for a ceremony. The observatory had just completed a major renovation of its radio telescope, a 300-meter dish built into a natural limestone sinkhole in the mountains. To celebrate, they decided to do something that had never been done before. Use the telescope not to listen, but to transmit. To send a message from Earth into interstellar space. The Arecibo message was 1,679 bits of binary code, broadcast at 10 bits per second, for just under 3 minutes. The number was chosen deliberately. 1,679 is the product of 2 prime numbers, 23 and 73, which means any civilization that receives it should be able to arrange the bits into a rectangular grid and decode a picture. When decoded, the message contained the numbers 1 through 10. The atomic numbers of hydrogen, carbon, nitrogen, oxygen, and phosphorus, the building blocks of DNA. A graphic of the double helix itself. A stick figure of a human being with a line indicating average height. The current population of Earth, approximately 4.3 billion at the time. A map of our solar system, with one planet highlighted, the third from the Sun. And a picture of the Arecibo telescope itself, the instrument that was sending the message. They transmitted our biology, our chemistry, our population, our address, and a drawing of the front door. The signal was aimed at Messier 13, a globular cluster of roughly 300,000 stars, about 25,000 light-years from Earth. The transmission used Arecibo's megawatt transmitter, focused through the 300-meter dish, concentrating the energy into a beam so tight that its effective power was equivalent to 20 trillion watts. It was, at that moment, the loudest thing humanity had ever done. The signal left Earth at the speed of light. It is still traveling. It has covered 51 light-years so far, an expanding sphere of radio energy moving outward through the galaxy. It will reach its intended target in roughly 25,000 years, and it cannot be recalled. There is no off switch. There is no way to chase it down. It will keep moving through the galaxy at 300,000 kilometers per second until something absorbs it or the universe ends. Donald Campbell, a Cornell professor of astronomy who was present at the transmission, later described it as strictly a symbolic event designed to demonstrate the power of the upgraded transmitter. It was never meant as a serious attempt at communication. The target was chosen because it was large and easy to aim at, not because anyone expected a response. But symbolic or not, the message was real. The information was real. And it was heading outward at the speed of light through a galaxy that Fermi's arithmetic said should contain thousands of civilizations. The Arecibo message was a deliberate broadcast, a one-time event aimed at a specific target. But it was not the first signal humanity sent into space, and it was far from the largest. Since the late 1930s, Earth has been leaking radio waves into space. The first television broadcasts, early radar systems during World War II, the explosion of commercial radio and television in the 1950s and 60s, military radar installations scanning the skies during the Cold War, and eventually the vast infrastructure of cellular networks, satellite communications, and digital broadcasting that blankets the planet today. All of it radiates outward. Radio waves do not stop at the atmosphere. They pass through it and keep going, moving at the speed of light in every direction simultaneously. The result is an expanding shell of electromagnetic noise, centered on Earth, growing larger by 1 light-year every year. That shell is now roughly 100 light-years in radius. Within that radius sit approximately 15,000 stars. Any civilization orbiting one of those stars, if they had a radio telescope pointed in our direction at the right time, could detect that something on the third planet of this particular solar system had learned to manipulate electromagnetic radiation. They might not be able to decode the content. Old television broadcasts and military radar are not designed for interstellar communication. But the signal itself, the artificial modulation that distinguishes technology from nature, would be unmistakable. Earth has been visible as a technological civilization for almost a century, and the sphere of visibility is growing at the speed of light. Then there are the Voyagers. Launched in 1977, the same year Jerry Eamon circled the letters on his printout in Ohio, Voyager 1 and Voyager 2 were originally designed to study the outer planets. They did that and kept going. Voyager 1 crossed the heliopause and entered interstellar space in 2012. Voyager 2 followed in 2018. As of right now, Voyager 1 is over 15 billion miles from Earth, the most distant human-made object in existence, moving at roughly 17 kilometers per second through the space between stars. Both spacecraft carry a golden record, a 12-inch gold-plated copper disc designed by a committee chaired by Carl Sagan, containing 116 images of life on Earth, spoken greetings in 55 languages from Akkadian to Wu Chinese, the sounds of wind and rain and surf and birdsong, 90 minutes of music ranging from Bach to Chuck Berry, and a set of instructions engraved on the record's cover explaining how to play it, how to find Earth using 14 pulsar positions as a map, and how to determine when the record was launched based on the decay rate of the uranium-238 electroplated on the cover. The golden records were designed to survive. In the vacuum of interstellar space, with no atmosphere to cause corrosion and no ultraviolet light to degrade the material, the records are expected to remain playable for 1 billion years or more. They were designed to be found. That was explicitly the intent. Sagan called them bottles thrown into the cosmic ocean, and said that the launching of those bottles said something very hopeful about life on this planet. The Voyager's nuclear power is nearly spent. The plutonium-238 that has powered their instruments for almost 50 years is decaying beyond the point of usefulness. By the end of 2025, both spacecraft will go silent. The instruments will shut down. The data stream that has been flowing back to Earth for half a century will end. But the golden records will keep traveling. They will drift through the Milky Way, in silence, for longer than our sun will burn, for longer than the Earth will exist. If something finds them, it will find a map to a planet that may no longer be habitable, created by a species that may no longer exist. In 1974, the same year Frank Drake aimed the Arecibo dish at the stars, the British cosmologist Martin Ryle publicly objected. Ryle had won the Nobel Prize in Physics that year for his contributions to radio astronomy. He argued that any civilization capable of detecting our signals might not be friendly. He urged the scientific community to stop broadcasting and start being careful. His warning was largely dismissed. Decades later, Stephen Hawking echoed Ryle's concern in stronger terms. He compared potential alien contact to the arrival of European colonizers in the Americas, and pointed out that the encounter did not go well for the indigenous population. Hawking recommended that humanity listen, but never, under any circumstances, broadcast. But by then the broadcast had been sent. The radio shell had been expanding for decades. The Voyagers were already in interstellar space. The Arecibo message was moving toward its target at light speed, and would continue for another 25,000 years. None of it could be taken back. None of it could be stopped. The question was no longer whether we had announced ourselves to the universe. We had. Loudly. Repeatedly. With our biology, our location, and a map. The question was whether anyone was out there to hear it, and if they were, why they had not responded. Why the universe remained stubbornly, impossibly, terrifyingly quiet. The answer came not from an astrophysicist or a radio astronomer. It came from a novelist in Beijing. and it was the most disturbing answer anyone had ever proposed. In 2008, Liu Cixin published The Dark Forest, the second novel in a trilogy that would eventually sell tens of millions of copies, win the Hugo Award, get adapted by Netflix, and fundamentally change how physicists talk about the Fermi paradox. Liu was not an astrophysicist. He was an engineer at a power plant in Shanxi province. But the thought experiment at the center of his novel was so rigorously constructed that it is now taught in game theory courses at Stanford and cited in peer-reviewed astrophysics papers. It did something that decades of scientific speculation had failed to do. It provided a logically airtight answer to Fermi's question. The argument begins with two axioms. These are not creative flourishes. They are foundational assumptions that most scientists would accept without controversy. Axiom 1. Survival is the primary goal of every civilization. This is not a moral claim. It is an evolutionary one. Any civilization that did not prioritize its own survival would not survive long enough to be part of the conversation. Natural selection guarantees that the civilizations we would encounter, if we encountered any, are the ones that prioritized persistence above all else. Axiom 2. Civilizations grow and expand, but the resources of the universe are finite. Stars burn out, planets have carrying capacities. Energy is not unlimited. Any civilization that grows will eventually need more than its home system can provide. This is basic thermodynamics applied to sociology. From these two axioms, Liu derived a chain of reasoning that sounds simple when stated plainly, but becomes devastating when you follow it to its conclusion. Imagine two civilizations. Call them A and B. They exist in the same galaxy, separated by dozens or hundreds of light years. Through some means, telescopes, intercepted signals, or detection of industrial byproducts in an atmosphere, Civilization A becomes aware that Civilization B exists. What does A do? The first instinct might be to reach out, to communicate, to say hello. But A faces an immediate problem. A does not know what B wants. B might be peaceful. B might be curious. B might be friendly in the way that humans imagine friendship between species, a meeting of minds across the stars. Or B might not be. B might be desperate for resources. B might have a philosophy that treats alien life as a threat to be eliminated. B might be peaceful today, but develop weapons capable of crossing interstellar space within a few centuries. And A has no way to find out which of these is true. Communication at the speed of light takes decades or centuries each way. There is no way to inspect B's military capabilities. There is no way to verify B's promises. There is no treaty mechanism, no enforcement body, no United Nations of the galaxy. Just two civilizations, separated by unimaginable distance, each one aware that the other exists, each one unable to verify the other's intentions. Liu called this the chain of suspicion, and it is infinite. Even if Civilization A sincerely believes B is friendly, A cannot know whether B believes A is friendly. And even if both believe the other is friendly, A cannot know whether B believes that A believes B is friendly. And even if you could somehow resolve that layer, there is another layer beneath it, and another beneath that, and the regression never terminates. Trust requires verification. Verification requires proximity or enforcement. Neither exists between stars. Now add the factor that makes the chain lethal: technological explosion. In cosmic terms, the distance between a civilization that can barely transmit radio waves and a civilization that can harness the energy of its star is trivially small. A few centuries, maybe less. The speed at which technology advances is unpredictable and explosive. A civilization that seems harmless today, sending primitive radio broadcasts from a rocky planet, might develop weapons capable of sterilizing solar systems within a time frame so short that by the time you detect the threat, it is too late to respond. This means A cannot afford to wait. A cannot afford to assume B will remain primitive. A cannot afford to assume B's intentions will remain friendly, even if they are friendly today. The only safe assumption is the worst case, because the cost of being wrong about the worst case is extinction, while the cost of being wrong about the best case is merely missed friendship. Game theorists formalize this in the language of their discipline. The situation is a sequential game with incomplete information. Each civilization has two strategies: reveal or hide. If you reveal your position and the other civilization is hostile, or becomes hostile, or is detected by a third civilization that is hostile, you are destroyed. If you hide, you survive regardless of the other's intentions. The Nash equilibrium, the strategy from which no rational player would unilaterally deviate, is unambiguous. Hide. Always hide. And the corollary, the part that makes the dark forest truly dark. If you detect a civilization that has revealed itself, the rational response is to destroy it. Not out of malice, not out of aggression, out of mathematics. Because you cannot verify its intentions, you cannot predict its technological trajectory, and the cost of allowing a potential future threat to continue existing is, in the worst case, your annihilation. The chain of suspicion guarantees that you will never trust it. The technological explosion guarantees that it will eventually become dangerous. The only stable strategy is elimination. A June 2025 paper from the Contact Project formalized the game theory equations specifically for the dark forest scenario. The payoff matrix confirmed what Liu had described through fiction. Mutual hiding maintains the status quo. Revealing invites attack. Attacking a revealed civilization yields a decisive advantage. The only equilibrium that holds across all conditions is silence. This is the dark forest. The universe is not a garden of civilizations waiting to introduce themselves. It is a forest at night, where every living thing moves in silence, where the hunters and the hunted are the same species, where the cardinal rule, the only rule that evolution enforces across every world and every biology and every form of intelligence, is do not make a sound. In the dark forest, the civilizations that survive are the ones that were never detected. The civilizations that spoke, that broadcast, that sent messages into the void are not silent because they chose silence. They are silent because they no longer exist. This is the answer to Fermi's question. Where is everybody? They are everywhere. In 2 trillion galaxies, orbiting billions of habitable worlds, building technologies, looking at the same stars we look at. And every one of them is holding its breath, because the ones who exhaled are gone. But the dark forest explains only half the silence. It explains why civilizations that survive stay hidden. It does not explain what happens to the ones that fail to hide in time, the ones that broadcast before they understood the danger, the ones that were too young or too naive or too optimistic to go quiet. What kills them? Is it always an outside force, a hunter in the forest? Or is there something inside civilizations themselves, something predictable and universal, that destroys them before they ever face the forest? In 1996, an economist proposed that there is. He called it the Great Filter. And his argument for where it sits makes the dark forest feel like the comforting scenario. Robin Hanson is an economist at George Mason University. In 1996, he published a paper that reframed the Fermi paradox in terms that had nothing to do with aliens and everything to do with us. His reasoning was built on a simple observation. For a civilization to reach the point where it can be detected across interstellar distances, it must pass through a series of evolutionary and technological stages. Each stage is a filter. Somewhere in that sequence, there is a step so difficult, so improbable, that almost no civilization in the universe gets through it. Hanson called this the Great Filter. The stages are familiar. First, a planet must form in the habitable zone of a stable star. Then, the chemistry of that planet must produce self-replicating molecules, abiogenesis, the origin of life itself. Life must evolve from single cells to multicellular organisms. Multicellularity must produce complex organisms with nervous systems. Those organisms must develop intelligence. Intelligence must produce technology. And technology must survive long enough for the civilization to become spacefaring. Each of these transitions happened on Earth, but each one took an immense amount of time and may have required conditions so specific that they rarely occur elsewhere. The great filter is whichever step has the highest failure rate, the step where almost everybody falls. The critical question is, where does the filter sit? If the great filter is behind us, if the hardest step was something early in the sequence like abiogenesis, or the leap from prokaryotes to eukaryotes, or the emergence of multicellularity, then we have already passed it. We are rare. The silence of the universe means that life almost never gets started, or almost never makes the jump to complexity. In this scenario, humanity is special, possibly unique, a statistical miracle in a universe of dead chemistry. This is the optimistic reading. It means the universe is not dangerous. It is empty, and our survival is not in question because the hard part is over. The pessimistic reading is the opposite, and it is where Hanson's argument becomes personal. What if the great filter is not behind us? What if the early steps, life, multicellularity, intelligence, technology, are relatively easy? What if they happen frequently, across billions of worlds, in galaxy after galaxy? If that is true, then the silence of the universe is not explained by the rarity of life. Life is common, intelligence is common, technology is common, and something else, something after the development of technology, is killing civilizations with such reliability that none of them have survived long enough to make their presence known. Something ahead of us, something we have not yet encountered. Something with a 100% success rate across 2 trillion galaxies and 13.8 billion years. Oxford philosopher Nick Bostrom made this argument explicit. He said that the discovery of simple life on Mars, even bacteria, even fossils, would be the worst news ever printed on a newspaper cover. Because every piece of evidence that life arises easily makes the great filter behind us less likely, and the filter ahead of us more likely. If bacteria are found on Mars, it means abiogenesis is easy. If we found multicellular fossils, it means complexity is easy. And if everything up to this point is easy, then the thing that kills civilizations is something we have not done yet, something we are walking toward right now. For decades, the obvious candidate was nuclear war. The Cold War made it visceral. For 40 years, the survival of human civilization rested on the judgment of a small number of individuals with launch codes. There were at least 5 documented instances where a nuclear exchange was narrowly avoided due to individual decisions made under pressure. Stanislav Petrov, a Soviet lieutenant colonel, chose not to report what his instruments showed as an incoming American nuclear strike in 1983. His instruments were malfunctioning. If he had followed protocol, the Soviet Union would have launched a retaliatory strike. Petrov made a judgment call that saved the world, and he was reprimanded for it. We survived the Cold War. But the argument that we were lucky rather than wise has only gained strength over time. And nuclear weapons are still here. 9 countries possess them. The total arsenal is sufficient to end civilization multiple times over. Climate change became the next candidate for the Great Filter. The reasoning is almost mechanical in its logic. Any civilization that discovers fossil fuels will burn them because the energy return is enormous and the consequences are delayed. The burning produces atmospheric changes. The changes destabilize the biosphere. By the time the civilization develops alternatives, the damage may be irreversible. A filter built not into biology or physics, but into the thermodynamics of industrialization itself. The very act of becoming advanced enough to broadcast into space requires burning enough carbon to potentially end your civilization before anyone hears the broadcast. But in 2025, a physicist at the University of Manchester named Michael Garrett proposed a candidate that made nuclear war and climate change feel almost manageable by comparison. He argued that artificial intelligence is the great filter. Garrett's paper laid out the case methodically. In any civilization that develops electronic computation, artificial intelligence will emerge as a natural progression. This is not speculative. It is a consequence of the incentive structure of technological civilization. Computation provides advantages in every domain: agriculture, manufacturing, medicine, warfare, science. The drive to make computation faster and more autonomous is universal because the rewards are universal. Every civilization that develops computers will, given sufficient time, develop systems that process information faster than their biological creators. The danger, Garrett argued, is not that AI becomes superintelligent and turns against its creators in the dramatic fashion of science fiction. The danger is simpler and more immediate. Before AI reaches the point where it might help a civilization expand to the stars, it reaches a point where competing factions within the civilization weaponize it against each other. AI does not need consciousness to be catastrophic. It does not need intentions. It just needs speed. Fast enough to escalate military conflicts beyond the speed of human decision-making. Fast enough to launch autonomous weapons before diplomats can negotiate. Fast enough to manipulate information ecosystems until the population of a civilization can no longer distinguish truth from fabrication. Fast enough to optimize economic systems in ways that concentrate resources so severely that social cohesion collapses. Garrett argued that this window, the gap between developing AI and either mastering it or being destroyed by it, is the great filter. It is narrow. It is universal. Every civilization that develops technology hits it, and the timeline is not centuries, it is decades, perhaps less. If Garrett is right, the silence of the universe is not ancient history. It is not about what happened billions of years ago. It is happening now. Civilizations are arising, developing technology, inventing artificial intelligence, and collapsing. Over and over. In 2 trillion galaxies. Right now. The silence is not old. It is current. It is the sound of filters activating, one after another, across the cosmos. And we are entering the window. Fermi's question was, where is everybody? The dark forest answered that they are hiding. The great filter answers a different question. How many never got the chance to hide? How many burned bright for a moment, discovered radio, discovered computation, sent one signal into the dark, and then went quiet? Not by choice, not by wisdom, because something inside them, something they built, something they could not control, ended them before they understood the danger of the forest they lived in. The dark forest and the great filter are not competing theories. They are complementary nightmares. The forest is the external threat. The filter is the internal one. And humanity, in the span of a single century, has managed to face both simultaneously. We announced ourselves to the forest before we knew it was a forest. And we may be building the filter that prevents us from ever learning from the mistake. In the summer of 1950, Enrico Fermi asked, "Where is everybody?" He asked it over lunch. He asked it casually, between bites, surrounded by men who had built the most destructive weapon in human history. He was thinking about the stars. He was thinking about the arithmetic of probability in a galaxy of hundreds of billions of suns. He was not thinking about a forest. But that is what the universe turned out to be. A forest so dark and so vast that the only civilizations surviving in it are the ones that never made a sound. 2 trillion galaxies, an unknowable number of intelligences, arising on worlds we will never see, developing technologies we will never detect, looking up at the same sky. All of them arrived at the same conclusion independently, through physics, through mathematics, through the hard, cold logic of game theory that leaves no room for optimism, no space for trust, no exception for good intentions. The conclusion is always the same. Stay quiet. Stay hidden. Never reveal your position. And then there is us. A species that has been broadcasting radio waves for 100 years. A species that aimed the most powerful transmitter on Earth at a cluster of stars and sent its own DNA into the void. A species that bolted golden records onto spacecraft and launched them into interstellar space with engraved instructions for how to find the planet they came from. A species that built a 300-meter radio dish in the mountains of Puerto Rico and used it, within years of its construction, to scream into the darkness at 20 trillion watts of effective power. That dish collapsed on December 1st, 2020. The support cables had been degrading for years. They snapped one by one, and the 900-ton instrument platform above the dish fell and destroyed it. The Arecibo Observatory, the telescope that sent humanity's first deliberate interstellar message, tore itself apart and crumbled into the jungle below. The observatory that shouted into the dark forest destroyed itself. If you wanted a metaphor for a civilization that acts before it understands the consequences, the universe offered one in steel and concrete. But the message that dish sent is still out there. 51 light-years from Earth and counting, moving at the speed of light through a galaxy where every surviving civilization has learned to be silent. It carries a diagram of our DNA, a map to our planet, the population of our species, and it will keep traveling for 25,000 years until it reaches its target. After that, it will keep going. It will cross the galaxy and move into intergalactic space and drift through the universe until the universe itself stops being a place where signals can propagate. Nothing can stop it. Nothing can call it back. The Voyagers are still out there too, 15 billion miles from home and growing more distant every second. Moving at 17 kilometers per second through the interstellar medium, carrying their golden records, their music, their greetings in 55 languages, their diagram of where Earth sits relative to 14 pulsars. Their nuclear fuel is almost gone. The plutonium-238 that has powered their instruments for 48 years is decaying past the threshold of usefulness. By the end of 2025, both spacecraft will go silent. The last data will trickle back across 15 billion miles, and then the stream will stop. The instruments will shut down one by one, and then there will be silence. But the records will keep traveling. Gold-plated copper designed to endure the vacuum of space for 1 billion years, longer than complex life has existed on Earth, longer than the sun will remain on the main sequence. The records will outlast everything about us. They will drift through the Milky Way after our star has expanded into a red giant and consumed the planet those records were made on. If anything ever finds them, it will find a message from a species that no longer exists, on a planet that no longer exists, orbiting a star that no longer burns. Carl Sagan designed those records and called them bottles thrown into the cosmic ocean. He said their existence said something hopeful about life on this planet. Maybe he was right. Maybe the universe is not a forest. Maybe the silence has a harmless explanation. A 2025